Welcome. There we go. Recording in progress. Love to see it. Hello, welcome. Good afternoon. Trey, Michelle, thanks so much for joining. And for everyone else watching these on your own time, thank you for taking the time to do that. So just a quick recap, who we are, what we're doing, where we're going, and then we'll kind of dive into some topics here. So I'm Alexander Booth. I'm the kind of head facilitator instructor for this class. I've been doing these kind of data science boot camps for at least 5 years, kind of coming into this. So been a little bit different, kind of being more asynchronous, but again, glad we can have these virtual sessions. And you'll see me posting a lot in the forums and making videos and stuff as well. So we're here to support. It's not our first rodeo, and gonna excited to kind of have you with us on this journey here. 10 weeks is not a long time to really get that whole kind of overview of data science. So you're going to see we have like a pretty good breadth of content and then targeted depth specifically into machine learning, Python pandas, and this week kind of with databases. So where we are, where are we going, what are we coming from? The first couple of weeks of the boot camp, right, we started changing just the paradigm of the way that we think about data problems. Week one, we're thinking like a data scientist. Week two, we were thinking like a computer programmer, and why automation, why write code, why automate the boring stuff and kind of automate these processes. Week three was all about data acquisition as well as kind of data file formats. So I know it's very easy last week to get hung up in some of the specifics with HTML and beautiful soup and web scraping, but that's not really the idea behind last week. Big idea, data comes in many forms and sizes, right? It can be markdown languages like HTML or XML. It can be JSON, like from API responses. It can be CSVs or Excel spreadsheets, right? It can be kind of your rows and columns, your tabular data. And as part of the data ecosystem, the data estate that many organizations have in place, we need to have a plan and an architecture in place for ingesting all these different data sources, putting them somewhere, organizing them somewhere. And this week, you may have seen me throw out the single source of truth paradigm a couple times. But I'll load this data up into a single source of truth. And then from those data sets, we can start doing our data analytics and kind of data science. So you'll see over the last couple of weeks, we've been blending a couple of ideas. Last week, we also introduced kind of data types, right? Our columns that we parsed from web scraping were all text, and some of them needed to be dates or integers. We also introduced visualizations last week. We created a couple of line charts, stock price over time, for example. And we can start using those visualizations, those leaderboards to start telling data stories and driving data decision making or decision making, data driven decision making. So where are we this week and kind of where are we going next week? So this week is kind of a deep dive into SQL. It's a long week in terms of content. I'm going to share this screen over here. It's a long week in terms of content, but a lot of it is pretty click through. So what I mean by that is you should be able to watch the videos and then click through some of the labs. We'll do a quick example of that before we dive into our code here. But what I really want you to take away from week four is what is a database? Why is a database needed? How are databases used in the terms of data engineering as well as data science? And again, like where has databases gone in the 2020s, right? So we'll do a little bit of history today as well. You know, if this is your first time using SQL, then that's awesome. SQL is one of the foundational languages that you need to know in data science. So we're going to go through a lot of kind of basics here. My background is more machine learning engineering, but I have done a lot of work recently in data engineering for some big companies. So this is a passion of mine as well. So excited to kind of share some of these thoughts with you today. All right. So I don't really have like slides or anything. I just have like the code and the content to go over. But let's start with some of the ideas in terms of what is a database and why are databases needed. So the purpose of a database is to act as your single source of truth for your data estate, right? We want to have a single location where we can go to find and access our content or our data that we need. So this has happened to me a bunch of times. Let me know if you relate. But let's say you have data stored in an Excel spreadsheet or a Google sheet, right? It can be really difficult to kind of make a copy, send that to your boss, and then they're making edits in a copy. Maybe you're making edits in your spreadsheet, right? Or in a Google Sheet or a Google Doc, you have multiple people editing the same document. Maybe they're overwriting each other in cells. So you end up with kind of a pretty disparate source of truth, right? If I have a copy, you have a copy, and our boss has a copy, which is the real like revenue, right? Which is the real value that I need for like cost of goods sold or like I said, price or revenue or something if it's in multiple places. And same thing if multiple people are just have full right access to edit documents as well. Like where is the confidence or the trust in those values that we get? So I introduced this idea in week one, but the idea of like data trust or trust in your data platform, trust in the numbers that you're doing the analytics on, trust in your models. A lot of data science is actually building that buy-in and building that trust with stakeholders. So, again, from my own experience, I used to work for the Texas Rangers baseball club out in Dallas, Texas, and so that was one of our biggest problems. How do we get players and coaches or less technical stakeholders to buy in to the numbers, the recommendations that we are making, right? And sure, maybe they'll buy into a visualization, but then what is your trust as the data scientist? What is your trust in the data that you're making these models and visualizations on, right? So that's kind of the pivotal idea behind a database. Provide that single source of truth, provide that trust as this is where I am getting my information from. And hopefully the data that gets into my database is trustworthy, right? And so this is where you have a couple of different paradigms in roles. I mentioned earlier the idea of a data engineer. A data engineer is exactly kind of what it sounds like, right? How do I get data from my vendors, from my source, and how do I locate it, clean it, and put it into a, I was like, that scared me. How does that, hey Karen, good to see you. How do I get that data into
Sorry,
a database?
sorry, I'm late. I kept thinking it was 12:30 instead of 12.
No, all good. All good. Glad you can make it. We have Michelle and Trey on the line here. So just going over a quick kind of understanding of like ground setting of what is a database, why is it needed, all that good stuff. And then we'll dive into the history of it. So the role of a data engineer is typically to go get that data and put it into a database, right? And then your business analyst, maybe they're querying the database, making reports, etc. Data scientists are kind of viewed more as a unicorn in the space because as a data scientist, you should be able to use a database as a source. Go to your database, extract data, make your visualizations, make your models, make your reports. But a data scientist should also have the skills to go out and supplement that data with APIs or web scraping or FTP servers. And in my role as a data scientist, I've done plenty of data engineering. And as a data engineer, I've done plenty of work as a data scientist as well. So there's a lot of fuzziness in those responsibilities. But if you ever go check out LinkedIn, see the job post for data engineer, the data engineer's sole purpose typically is to go get data from source, clean it, prepare it, and put it into a database. You may hear this called ETL, which is an acronym that stands for extract data from vendor, transform it, clean it up, and then load it into a database or a data warehouse. I think Karen actually put a couple of ETL ideas into the forum threads for this week. So that's kind of the big role of a data engineer here. A couple other things before we get into the code for week four. I just wanted to give a quick timeline of database management systems, as well as kind of what is a relational database to begin with, right? So databases have actually been around for a long, long time. They've been around since the 1970s in kind of their first iteration. The leaders in the space here are going to be Oracle and Microsoft. Oracle, yeah, 1977, down in California. Larry Ellison, one of the richest men's in the world now. And then Microsoft SQL, like server and everything, they all came out kind of in this originally in the same time in the 1970s. And again, if you think about it, computing power is kind of on the rise. There's a lot more business demand, enterprise demand for a data storage solution. So Oracle and Microsoft SQL Server specifically, we're kind of first to market in a few of these. So one thing to note, these initial databases, these original databases are all relational. What that means is that they are a venue for storing structured data. So we'll talk about a couple different types of data in class over the next few weeks. But at a high level, you need to know that there are three main types of data: structured, semi-structured, and unstructured. Back in the 1970s and even going up to the 2000s, the main data that people could analyze was structured data. So this is going to be your rows and columns. This will be your reports. There's a structure to it, right? That's why it's called structured data. We have ID in row one, date in column two, and revenue in column three, for example. With structured data, it's pretty easy to store in a database, specifically a relational database. So again, definitions in the name, a relational database has tables that have relationships to each other. So for a quick example of this, let's look at um, I was gonna look at like the movie one, but I think this is probably a good one too. Yeah, so as customers and sales, I think this is a pretty easy one. Or products and orders, this is a pretty good one. Let me open this one up. So a relational database, right? It has structured data that have relationships to each other. So in this example, this database contains four tables. These four tables are structured, as in they have rows and columns, and they have relationships, right? I have a table of just my unique customers. I have a table of my unique employees. I have a table of unique products, and then I have a table that is my unique orders. And for each order, we have a customer who orders a product from an employee. So that's kind of where the relationships lie. Sure, you can have relational databases where your tables don't have any relationships to each other, but that kind of defeats the purpose. Relational databases are optimized to limit data storage. For example, we only want to store data once. We'll get to that in a second, as well as optimize queries against those data sets. If you just have large tables that don't necessarily need joins or have relationships to each other, then a relational database may not actually be the right use case. So again, remember back in the day, these databases are stored or created as applications. So just like Zoom or Steam or Microsoft Word, I guess, you would download and install a database on a single computer, a single server, and then you would be loading data into that database accordingly. So a big idea here is that size kind of does matter in this case, right? If my database is loaded on a machine that only has 8 GB of RAM, I'm not going to be able to store a lot of data, right? So we want to be efficient with our data storage. So that's why you'll see over here, where's my little red pen? I could have in my orders table the customer first name and the customer last name also in, or maybe even the product name as well, right? Why don't I have all of those values also stored in the orders table? And the answer is that it's inefficient. It's duplicate storage. Why do I need to store the first name of my customer in both the order table as well as the customer table? You don't, right? Instead, we can just store it once in the customer table. And if I need to know the most common last name of somebody to place an order, I join using the customer ID. I use the relationship established to connect orders back to customers, and then I can aggregate or group by or access the last name there as well. So that's big idea number one: limit your data duplication and your data storage. And then big idea number two is around data types. As you'll see, different data types require different amounts of memory to store. Strings or text typically take up the most amount of memory. This is because your computer may not know exactly how long this string is, right? If you just declare a column as an unlimited text object, then behind the scenes, the database is going to allocate a lot of memory to that one item. Numbers, on the other hand, such as integers, especially integers, they take up only a certain number of bits and typically a small amount of memory. So if I have the number 12, right, that takes up like 2 bits worth of memory. So it's a pretty small number. This is why you'll see integers used to establish your unique ID for a value. And it's why you're going to see IDs used as duplicate keys, right? We use IDs as the key to join tables together, right? So customer ID we can use to join orders to customers. Since we have to have a key that's duplicated, we'll have it as a number to minimize our memory footprint, right? So let's just pull it back to kind of big ideas we need to take from relational databases. Relational databases came out of the 1970s. They came out of a need for a single source of truth. These relational databases are really good at storing structured data with relationships. We want to minimize our memory footprint. We want to minimize our storage costs, and we want to be optimized for queries that have and are going across multiple tables using joins. The first relational databases you should know, Microsoft SQL Server, and Oracle. They were basically the kings of this area from the 1970s up to about the 1990s. In the 1990s, open source, so free, basically, free relational databases got kind of put into the market. The most popular of these being MySQL and Postgres. So MySQL and Postgres are two different relational data management systems, and they are open source. That's the big idea between this and Oracle and SQL Server. One other quick thing to note too, and this is kind of annoying, but it is what it is. A lot of these different databases, they all use SQL as a querying language, but they all use various flavors of SQL. I kind of do it as like, my metaphor here is like speaking Spanish, right? Spanish in Spain is different than Spanish in Mexico, which is different than like Spanish in Puerto Rico, right? So we have different like flavors of Spanish across these locations. Same idea with SQL. It's still SQL, it's still Spanish, but it's going to be a little bit different if you're doing it in MySQL versus SQL Server versus Oracle or something like that. We're going to fly through this because I got to write some code here. Through our open source databases, we then kind of came into the 2000s. And so with the 2000s came kind of this boon of big data, right? Big data meaning data started coming in other shapes and sizes. No longer did an organization just have flat structured files. We also needed to analyze JSON data, XML data, images, texts, reviews, right? We have all this other data coming into play. In the mid 2000s, this led to the rise of the NoSQL database. NoSQL just implies not SQL. It is a non-relational database. And so this is also kind of the foundations of the data warehouse, which we'll get to in the 2010s here in a sec. But big idea behind a NoSQL database is how do we store data that may not be structured, that may not have defined relationships between tables, etc. So big players in the space you need to know include MongoDB, which is basically a way to store JSON data. And you'll see that inside of a MongoDB, we have lists and dictionaries, and it should look a whole lot like your JSON that comes from APIs. All right, so now you can see a workflow. Make a request to an API, get back the data as this JSON object, store that JSON object in Mongo, and then when you get around to it, extract that data from Mongo, clean it up, flatten it out, define relationships, and then save that clean data into a Postgres database for use for business analysts downstream, right? So now we have NoSQL databases interacting and playing with relational databases as well. Other NoSQL databases you may or may not need to know include things like Neo4j, which is a graph database, which is kind of crazy. Definitely out of scope for this class. I think that's mostly it. We'll stop with there, I think. So then the 2010s happen. And when in the 2010s, the big idea is cloud, right? AWS became a big thing in around 2012. Microsoft Azure started going into the weeds and started promoting their cloud product in the late 2010s. So the big idea with cloud is instead of having to download and install an application on your laptop, why don't you just install it on a cloud computer? Or even better, Why don't you store it onto a cluster of computers all working together to do one thing, right? So this is called distributed computing power. So with kind of the age of cloud came the age of cloud databases. Cloud databases came in two shapes. The first shape was your classic Postgres, SQL Server, etc. But instead of being hosted on your server, it's being hosted on a cloud server, which typically meant you had more memory and you can even be bigger and kind of do more powerful queries. And then two, the second flavor of cloud databases came in the form of a data warehouse. A data warehouse uses this compute cluster idea that we mentioned earlier. With a warehouse, instead of being restricted by the size of your one machine that you've installed your database on, it can essentially be infinite, right? We can just keep adding more computer power to our cluster, and we can keep scaling horizontally to accommodate more data, to accommodate more complicated queries, etc. And with the rise of the warehouse, we're sort of consolidating structured and unstructured data. If you've done any of the Kaggles recently for week 4, you'll see that you play around with a data warehouse called Google BigQuery. Google BigQuery allows you to store JSON data as well as your structured data as well. So you can see you can actually work with JSON data within these kind of data warehouses. So no longer do you have to kind of keep these separate. So of course, you still have pros and cons. The pros of a data warehouse, you can consolidate all of your data in one place. You can scale it out infinitely. You can use as much compute power as you need. The limitations, though, are about twofold. The limitations first, cost, right? The cost of a warehouse is going to be pretty expensive, especially depending on how many computers you're using to power it. And the second limitation is going to be latency. With a warehouse, your queries are optimized to be going against terabytes of data, right? Big data. If you just have smaller data sets, then maybe a warehouse is overkill and it's slower to actually execute those queries on a warehouse versus a relational database or OLTP system. If you want to go really crazy down the acronyms, this is OLTP versus OLAP. OLTP being a relational database like Postgres, and OLAP being a analytical processing database such as BigQuery or Snowflake. And that's mostly what you need to know: the rise of on-prem enterprise relational databases to open source relational databases to NoSQL databases to cloud data warehouses. And then I got to throw it out there. In the 2020s, the new kind of data ecosystem includes things like the data lakehouse, which is a way to combine structured, semi-structured data with unstructured data. So typically in an old legacy solution, if you had a image, a video, a PDF file, you would have to store that separately from your database. But with the idea of a lake house, we can bring our data lake, which is typically where your unstructured data lives, with our data warehouse, where our structured and semi-structured data lives. And all of a sudden, we have one happy family where all three of our different data types all live together and are governed in one single source of truth, right? At the end of the day, we want to come back to that single source of truth. You may also hear things like data mesh thrown about, but data mesh is more like when you have multiple lake houses, like your finance team has a data warehouse, your accounting team has a data warehouse, your, I guess, R&D team has a data warehouse. A data mesh allows you to kind of cross-pollinate all those data warehouses with governance. So people only access the data that they need, but also across silos and across teams, which is pretty cool. All right, so that's the big idea for kind of week 4. Yeah, feel free to drop questions in the Zoom chat too, and I can circle back to them. All right, so hopefully you have a big understanding of why database systems and what is a relational database. So let's get into actually writing queries and designing these databases. The reason why SQL is so powerful is because SQL not only works right on your old school relational database systems like SQL Server and Oracle, but they also work with the Open source solutions like Postgres and MySQL. They also are the main language for the data warehouse. Snowflake, Redshift, BigQuery, Databricks, they all have their own flavor of SQL. And of course, the Lakehouse, data mesh, they can all be interacted with SQL as well. And what you'll find is that SQL can be used for also things like data engineering and even machine learning. I kind of love this. Let me just show you a quick art of the possible here. BigQuery, SQL, ML. This is pretty wild. You can use Google SQL. You can use SQL. Again, Google SQL is like their flavor of SQL, right? It's their Spanish. It's their flavor of Spanish. You can use their SQL queries to actually create and store machine learning models, which is pretty crazy, right? So this is why as data scientists, we need to be pretty familiar with SQL to both, of course, power database creation, but also to power kind of the outputs of databases and even to create Spark and machine learning workloads as well. So like I mentioned with week 4, they have a variety of labs just because of the length of the session. So if you go into like module set 4.3, for example, it's going to give you the option to open labs like this one. This lab is what I call a click-through lab. So you have a couple of options with these click-through labs. The first is exactly what I say and just click through it all, read what it's doing, look at the syntax, look at the table structures, look at the images, and kind of click all your way through. However, your other option is if you would actually like to run all these queries and kind of see what this looks like. Karen's actually put some information in the lounge, right? Yeah. I'll give you, do you want like a
Yeah,
minute
I did
here,
that.
Karen, just to kind of,
And actually, I just now posted, they have stuff for 4.8, I think it is. That looks more just like walkthrough. So I've also created the database that they describe creating, but in SQLite, and I could use as well.
so you have a couple options. I like walk through lab. Maybe that's better than click through. You have your option either walk through or click through those types of labs, or we've given you information here on how to actually access these databases and like attach them and run them and use them. And you can actually start running these queries on your own. So that's one option. Like I said, to me personally, I would rather you spend your time on the labs that we're going to review for the last hour or so here, which are going to be the Python labs where you also are practicing SQL. So the more hands-on labs. Those start in, I think, module set 11. So module 3 and 6 are all the click-through labs. The enrichment activities, anything that mentions IBM Cloud, I definitely recommend activating your trial account and playing on there, but just know that that is optional, and you shouldn't be charged, but it's also optional. You don't have to activate and interact with your IBM Cloud to get through this course. So that's another type of lab you may see in week 4. And then what I care about is when we get all the way down to module set 4.11, which is where we're going to start today.
If you want to do the IBM Cloud stuff, you can do a free tier as long as you stay within those limits. And most
Yeah,
things you'd
and
probably be doing here is probably will stay within those limits. The other thing well, my other little thing is I prefer the click through, as you called it, than the walkthrough because of its little live notebook. You can write new cells and play around, which you
yeah,
can't
and that's
do.
what
Well, it's
yeah,
just
and
a
that's what we'll
static.
see here. Yeah, with the lab starting in 4.11, you'll be able to interact and write your own code.
Yeah,
So
yeah. So anyway, but that's why I provide you could play around all you want, or you can
yep,
have a little sandbox. And what was else I was going to say? What is something else? No, I
the
forgot.
IBM Cloud. My thing on the IBM Cloud, I confirm that everything that in all the course sets, it should all be in free tier. So even if you do sign up and
Yeah.
give your credit card over, you shouldn't
Oh,
get
that's
any
what I was going to say is
charges related to the class.
when it comes to different dialects of SQL, most of it, pretty much everything we're going to be doing
ILX.
here is fairly foundational, so it's all going to be pretty much the same. So
Yep.
only when we get into more esoteric things, so you get difference between like, SQLite and PostgreSQL and Google SQL and all, they have those little differences. But as far as what we're doing, pretty much apply everywhere.
Yep. And then I've also ran through all the notebooks for Module 4 and backed them up on my GitHub, so you can get that information out of the forums as well. But yeah, for this class, I'm going to run through, if not probably not every single one of these, but all the way. This is the one I'm supposed to do today. So we'll start with the 411 ones and then probably skip over to 416. Fiona. All right. Cool. So all I've done so far, we've just opened the first lab here on 411. If you want to follow along again, this is kind of our hello world idea to our database. So again, make sure that we're connected to a kernel. I like to restart kernel and clear all outputs. And then for this code, we should just be able to run all cells. And we'll let this kind of spin up its thing. Cool. Great. So I think that worked. Cool. So one thing I wanted to note before we walk through what this code is doing, the first couple steps here where we are using a SQLite 3 database. SQLite is another type of database. It's an open source data for database, very similar to kind of Postgres or MySQL. However, the big idea with SQLite is that it is not an application. Unlike SQL Server, Postgres, whatever, which you have to download and install on a server, SQLite is basically a file format database. So it's loaded up the entire database as this file object called database.db. That .db indicates that this is a SQLite database. So SQLite's great. It's actually, because it doesn't need a server, this is actually what's used to power many of the applications on your phone. If you download Clash of Clans or whatever, it'll sync to a SQLite database locally on your phone as you play the app, and then kind of push that up to the cloud once you reconnect to Wi-Fi. That's also how you can like play your New York Times Wordle, or I guess it's not Wordle, but like the crossword or whatever without internet. And then when you turn your internet back on, it all kind of syncs back to each other. So SQLite is actually really widely used, especially for compact, small scale database use cases. Anyway, that's kind of what we've done here. We've used SQLite, the Python package, to help connect Python to SQL. We've connected to our database here. And within this database, we end up creating a table. So this is going to be known as CRUD operations. Throwing more acronyms at you. Acronyms you should know coming out of this. ETL and CRUD are some of the big ones. So CRUD stands for create, read, update, delete. I don't know. I just Googled the word CRUD. Uh, CRUD database. Create, read, update, delete. This is basically the idea that no matter kind of what database or dialect you're using, every database, data warehouse, data lakehouse will have these four foundational ideas. You can either create data, create a table, create a database, create a row. You can read data, select all the rows, select all the columns, select multiple tables, whatever, read data. Update, we can alter data already in our system. Update row X, change value, alter value to something else. And finally, delete something from my data lake, my data warehouse, my data table. Even just rows and columns as well can be deleted. So the very first activity here, we want to practice our CRUD operations against SQLite. You'll see here we are deleting a table, drop table. We are creating table, create table. This table has multiple columns in it, file name, L name, first name, last name, city, and ID. And we can see what the table is like. I guess more creates, insert this row, insert this row, and now a read. Select star from table, and we can see all the data that we have got. We have 3 rows here. Rav, Raul, and Hema are all located in my database. Cool. I think that's the most important here. Update. This is going to be our alter. update, we're going to change the row. We're going to set city to be Moosetown, where first name is equal to Rov. And now when we look at our data, we can see that Rov is now in Moosetown. So we've done a create, read, update, and we did our delete at the top. The last thing to notice, and I actually mentioned this last time as well, not only can we use pandas, right? What is pandas data frame? Main idea, we want all data stored as a pandas data frame to use for our analytics. It's a standardized data structure kind of within data science and Python to allow us to interact with data programmatically. So we talked about how pandas have different functions to read data from CSVs, JSON, XML, Excel, Parquet. Pandas can also read data from a SQL database. So here my query, select star from instructor, pandas.read that SQL query, and we end up with our data here as a pandas data frame. And with our data frame, we can then do whatever we want to it. So that's our little hello world introduction to CRUD, create, read, update, deletes, introduction to executing these SQL commands in Python and connecting it back into pandas. The other kind of, let me look at the other ones here. Yeah, these are worth going over real quick as well. So let me find the next one in module 411, SQL Magic. The big difference between these two notebooks, notice in the first Hello World notebook here, we were running and defining our query as strings, right? Text strings. And then we were using this SQLite cursor thing to execute the query. That's kind of pretty annoying and not a great user experience, especially just to write your SQL queries. And so what we want is we want to be able to utilize, we want all of that just to be taken care of behind the scenes, right? I want Python to know that, like, hey, this is going to be a SQL command, just execute it as SQL, right? So that's the big idea with these kind of SQL magic commands. We can actually build in and tell our Jupyter notebook to use SQL by specifying this magic command %sign SQL at the top of our cells. It's pretty great. I use this all the time in my Databricks notebooks as well. And again, you'll see this is a big idea that transcends week 4 just in data science, which is the idea as data scientists, we need to be able to write in both Python and SQL. And it'll be great to be able to do that in one location, in one type of notebook. So you'll see that in many notebooks out there through Databricks, AWS, Azure, whatever, they'll actually let you write Python and SQL in the same interface. So same idea here. Let's restart our kernel and run all cells. And if all goes well, we're going to create a new database called SQLite Magic. There it is. And then we're going to create tables. We're going to insert rows. And then we should be able to write SQL commands to extract the data from it. And then finally, we also show how you can utilize and connect Python to SQL, whether it's a variable, whether it's a response as a table, and then even making some visualizations off of this. So again, just from this, we can see that pretty good distribution of test grades, right? Remember, this follows the normal distribution, which we talked about in week 1. And maybe we skew a little bit poor on our grades. So maybe we should have done a better job prepping our students so they get better scores. Or maybe this is an incentive data-driven decision because maybe these scores are skewing a little bit low. Maybe we, what's it called? We rescale the grades so that everyone gets a little bit of a boost or something. Cool. That's the last most important notebook that I think I want to talk about here. We'll go over this one, but I'm not going to fill this one out yet. So this then gives us into our project for week 4, which is now that we know what SQL is, what a relational database is, we've practiced our CRUD operations, and we've talked about how to execute SQL commands in our Jupyter notebook. Let's actually do some real work, right, with our data sets. So our goal is to analyze data, census data, crime data, and school data from Chicago and around Chicago, and write queries to analyze and answer that information. So we'll start with this one, which I recommend you do on your own time, and finish up these quick questions. We're going to maybe do one or two here just as a hello world, make sure that everything works, and then we'll pivot over to the big activity to do together. Cool. So let's do this. We're creating and connecting our table. I'm commenting out this pip install of pandas. Pandas is already installed, so you shouldn't have to do that. And then we're going to tell our Jupyter notebook that we're going to be connecting. Whenever we write a SQL command, we're going to be connected to this database location. Let's first do some CRUD operations. I love this one command because it shows like the power of pandas here. Um, this is awesome. So what are we doing here? We are creating a table, but we're creating a table first by making a request. We are loading a CSV from the city of Chicago's cloud server, so like an FTP server. We load in the CSV from our data vendor into a pandas data frame, and then we write that data out. We create that data as a table called Chicago socioeconomic data. So that's data engineering. Look at you doing data engineering in a data science bootcamp. But we are grabbing data from a vendor, saving it, and then putting it into a database for that single source of truth logic. So if I run this, this should work. And cross your fingers. Yay, we got something. I think it's this one right here, socioeconomic.db. And if you're curious, we can actually look at this data. And you can see that we have about 78 rows, so it's a pretty small data, but it's about 78 rows here. And it looks like that worked pretty well. So let's double check that this works. Let's write a select star command. So a read, select all rows and all columns, or select all columns from this table, limit 5 rows. And when we run that, we get this beautiful little table that popped out here at the end. So same idea, select count star, count of rows from my table. And we have 78 rows. We can validate that again from our pandas data frame above. Next one, how many community areas have a hardship index greater than 50? I'm going to use the double percent sign SQL command because I like writing multi-line SQL statements. Select star from table, and we're going to use a where clause here. Where the hardship index column is just called hardship index, where hardship index is greater than 50. If I execute that, it brings back all the rows where this is true, but they just want the number, so we can do a count of star. So 38 rows should hopefully have that hardship. Oh, yay, let's go. We got it right. We'll do, just do one more here. What is the max? I don't want to do that one though. Let's do which community area has the highest hardship index. So same idea, select star from Chicago socioeconomic data, where hardship index equals, and this is where I need my equal sign to be dynamic. I want the hardship index to be equal to the max hardship index. So sure, we could hard code that with the actual number. Maybe it's like 91 or something. 98. But that's not really what we want to do. What if a new row comes along with a worse hardship index? We don't want to have to break these downstream queries with that dependency. So instead, what we can do is what's called a subquery. This is where we use multiple queries in one big query. It's also another way you can do joins as well. But in this case, we're going to be where hardship index equals, and this is where I'm going to write my subquery. Let me zoom in. Where hardship index equals, select max hardship index from my table. And if this goes right, we see that Riverdale has that hardship index of 98. Let's limit the number of columns we bring back. So let's bring back CA, community area name, and the hardship index. And we should see that we have Riverdale, which is 98.0. This CA is just the ID. It's the community area ID. It's just named pretty bad. All right, so now we've practiced running queries here as well, which is great. So let's pivot over. I want to spend 15 minutes writing some live queries on the big data set, and then kind of leave 15 minutes before 2:30 Central for y'all to ask any questions. If you have to hop early too, that's totally fine. I know these typically are only supposed to go an hour, but we have an hour and a half kind of blocked, which I like to make use of. Just say bye in the chat if you hop off early or on time, I guess. Um, let's see, 413, yeah, that's like a project. Cool. So we reviewed all the activities in 411. The 413 one is pretty good. It introduces another table for the school table, which is going to be just information around like school performance. It's going to be very similar to what we just did in this last example in 411. Load in a table, write some queries against it, just get a quick understanding of it. The whole lab for Module 4 culminates in the 416 activity. So this is your like main takeaway from the module. In this activity, we're going to work with all three data sets, the census data that we just kind of looked at, the school data, and then a new data called crime. And we're going to be loading all three of these tables up and then writing some queries against them as well. So if you haven't done 416 yet, no worries at all. You have until the end of the week, but feel free to watch or work on it now with me if you want to be hands-on, or watch this video back later if you get stuck. What I like about 416 is that it doesn't give you the answers. Ha. So yeah, before this class, I had to spend the time myself to write all the answers. So if you creep on my GitHub, you'll see that I do have all the answers here. But unlike the other notebooks where you can just click on a button and it'll tell you some of the answers, this one does not. Womp womp. Just kidding though. No, I'm not kidding. It doesn't give you the answers, but I will help you out over the next kind of 20, 30 minutes here. All right, let's get after it. I recommend having one of the other activities open at the same time. So I'm going to actually open up that last activity that we just did, just because there's a lot of similarities in the initial code to load up the database and then start setting up the queries. So I'm gonna have two tabs open. The first is going to be what we just did in 411. You could also use the 413 example here as well with the school data. Oh my God, this one. And let's just start going here. So it gave us the URLs we need to load in all three of the CSVs. The pip installs, I don't think we really need those either. So I'm gonna comment these out actually. Actually, I'll keep, it's fine, whatever. We'll just leave it in, I guess. But you definitely know I'm pretty sure you don't need these. Hopefully that doesn't break anything. And boom, cool. And here's the old example we just looked at. Yep, cool. All right, so our first question here is, hey, we need to load our libraries. We need to create a new database called FinalDB, and then we need to load up all the CSVs. So let's go ahead and do that again. I'm going to rip this from the last activity. We want to load pandas, import pandas as PD, import SQLite 3, and then establish a connection to finaldb.db. That's going to be this command right here. And our database is called finaldb.db. Cool. So that should be able to run. And now we can load up the SQL Magic module, which is this load extension. And then next thing we need to do is load in the CSVs accordingly. So let's go ahead and do that. This will actually require 3 different cells. So our first table is going to be the census data. And the URL for our census data is this URL right here. So I'm just going to highlight this whole link and copy it and then paste it down here. So Pandas should be loading that CSV and then loading it to SQL. And just for a sanity check, we can print the df.shape just to make sure that we loaded some rows and columns. So see if this works. We end up with our 78 rows, and then we load it in the table. I'm going to create 2 more columns here. I'm going to hit this plus icon at the top to do that. So we need to do this 2 more times. The second table is the school table. The third table is the crime data. And let's go ahead and grab those URLs as well. Schools. Boom. And the crime data, let's grab that as well. Boom. Look at that. Love me a little bit of live coding in the afternoon here. Run the public schools 566 rows and crime data 533 rows. So we should have loaded up all 3 CSVs and then written them to our table. And then finally, we need to establish the connection between the database and our magic command, which is going to be this guy right here. And we'll call this finaldb.db. And that should hopefully work. So all of that is our data engineering, right? We went out to our vendors, we loaded our vendors' data into a data frame, and then we saved those data frames as tables to our relational database system. Note that this could be XML file, it could be a JSON API, it could be a web scraping document. It doesn't really matter, right? Get your data from vendor, clean it up, standardize it, and then put it into a single source of truth. That's the first big idea here. So now let's start writing some queries. Find the total number of crimes recorded in the crime table. Again, I'm going to do the multi-line SQL command because I like writing in multiple lines. The way I typically start writing a SQL query, I always start with a select star, even if we're going to change the star. This is because the most important part of the query is the from clause. Where are you getting your data? And then any other kind of clauses like where or order by or group by, etc. So we're going to select star from. The crime table is going to be our Chicago crime data table. And if I just want to see what this looks like, I can go limit 1, and that's going to return just 1 row of data, which will also show me all the column names for it. To actually answer the question here now, we can say I want to know the count of star, or you could even do count of ID or count of case number as number of crimes. I'm aliasing my result here. That alias means that when the response comes back as a table, it's going to be viewed as the column name. So when I run this, you'll see that the column name now becomes num crimes. If I didn't alias this, Notice the column name here is just count of ID, which is a little bit cumbersome for doing like more robust analytical like commands. So that's why we like using aliases, provide that human digestible as well as scalable column name for downstream analytics. This also is passing my gut check. 533 is the same number of rows that we wrote. So yay, we have 533 crimes. Cool. We'll probably not have as much explanation for some of these other ones. List community area names and numbers with a per capita income less than 11,000. That is going to be coming from the census data. So let's do the same thing. Let's just look at the first row of the census data. And we should be able to see that we have community area number, community area name, and per capita income, which looks to be a number already. So we should be able to write our query now. Select star from census data where my per capita income is less than 11,000. And then I'm going to do an order by, and let's order by the, maybe let's just order by per capita income ascending. So we're going to have the lowest one first. Next, let's grab the columns that we need. Community area number, that's the ID, community area name, and of course, our per capita income. Notice I'm not aliasing anything here because these columns are already pretty descriptive. Aliasing is only really used with like analytical commands such as max, sum, average, etc. Cool. So this lists 4 and Riverdale is the lowest one. And I think that's the answer. I think it's just 4. I'm cheating. I'm looking at what I did last time. Here's the one I did earlier. 1, 2, 3, 4. Beautiful. Good job. Passed me. All right, let's do a few more here. Yeah, we've got 12 more minutes. List all case numbers for crimes involving minors. This is a fun one. Not a fun one. It's a good it's not a fun question, but it's a fun query to write. All right, so let's select, I'm just going to do a select star from our crime data. And now we get to our where clause. For our crime data, the case involving minors will happen in the description. So let's check if the word minor appears anywhere in the description of our crime. So it should be something like where the word minor or where description is like is a special keyword in SQL for fuzzy matching or matching partial strings, where description is like any number of characters, then the word minor, and then any other amount of characters. So this is kind of wonky syntax, but it basically is saying select all rows and columns from Chicago crime data where description contains the 5 letters of minor. And now we can bring back some, like maybe some columns instead. And let's bring back, and then maybe the location description. Cool. And maybe we do an order by date ascending or descending. Cool. So we can see here there were 2 cases that involved minors, selling liquor to minors, and then consumption by minors. So those are the only 2 here in this analysis. Cool. Let's do the next one. So let's all kidnapping crimes involving a child. This is going to come from primary type, I think. Yeah, primary type. Oh, look at me being fancy. Let's do that. So let's do primary type like kidnap. And we have one kidnapping case. And if we wanted to be more specific to only look at child abductions, we could say, and I want my description to contain the word child. And this still returns the same row, right? We have kidnapping and child abduction. List the kind of crimes that were recorded at schools. So let's do same kind of idea, but now we're going to be parsing against the location description. Location description like the word school. And we can see all the different, I guess, crimes here. I like this example, but the actual question just lists what are the unique kinds of crimes. So to do that, we get to do another little fun thing. Let's only select the primary type and the description. And now I'm going to use the keyword distinct. Select the distinct primary type description combinations where the location description like school. And we see we have a lot less rows here. And then maybe we can order by, in this case, let's order by primary type as well as the description. So I'm just ordering alphabetical. And so here we go. Assault, battery, criminal damage to vehicle, to land, narcotics, and a public peace violation are the unique types of crimes at my school. I may leave a couple of these as an exercise for the reader. List the type of schools with the average safety score for each type. Let's see if we may keep flying through these. List the type of schools along with the average safety score for each. So for this one, we need to use the school data. So this is our third data set. So let's take a quick look at what this looks like. Our school data is called Chicago Public Schools. And we see that this is all the different columns and things in my school or my school data. So we are looking for the type of school translates to this column right here, whether it's an elementary school, a middle school, or a high school. And what we want to do is we want to group by that column name and then look at where's the safety score? Safety score, there it is. And we want to look at the average safety score for each of those types. So let's see what this looks like. Select star from Chicago Public Schools. Group by, we're doing an aggregation. Group by the column elementary, middle, or high school. Notice because this contains foreign characters like spaces and commas, I'm going to use backticks to assign it as a column in my query. And we need to return this as well as the average of the safety score, which is just AVG safety score. Notice because this is an analytical calculation, I'm going to alias this as average safety score. I'm also going to alias this as well because it's a pretty obnoxious column name. Type of school. Awesome. And then for completeness, we'll do an order by. We'll order by the average safety score descending. So we'll go from safest to least safe. So high school, then elementary school, and then middle school. So again, maybe thinking critically like data science, this actually doesn't make that much. It's surprising. I would say that elementary schools should by far be the safest, and maybe high schools are the least safe. But maybe that's not what this data is telling us. And then maybe these are the types of questions you should ask your data to then foster follow-ups, right? Maybe we can now do a further analysis to see maybe why high schools are have this high safety score, at least comparatively, in Chicago. All right, a couple of these are more duplicated. List the 5 community areas with the highest percent of households below the poverty line. We're going to go back to our census data and looking at our census data. We want percent of households below poverty. That is the name of it. Select star from census data. People have also asked in the past, like whether or not capitalization or tabbing matters. With most SQL dialects, it doesn't, right? The capitalization and the tabbing don't matter, but it is best practice because it makes it easier to read from other people that are looking at your documents. Actually, we're not doing a where clause. We want to group by community area number. So the ID of the community neighborhood, as well as the community area name. And then we want to select the max of that, maybe. I feel like I don't even need to do a group by. Is it unique per community? It probably is. Order by this guy, descending, and then limit 5. So Riverdale, Fuller Park, Englewood. I think I don't need a group by here because we have only one row per community anyway. Oh, I had to do a group by. Doesn't really matter. I'm pretty sure you don't need to do an aggregation, but whatever works. Which community area is the most crime prone? I love this question. This is my favorite question here. So if you're gonna pay attention, this is the only one I want you to pay attention to. We're gonna be doing a join. Yay. We gotta connect 2 tables together. So we're gonna be connecting the crime data to the community area. If I look at both of those tables, you'll notice that in my crime data, I'm gonna actually have a column for community area number. This is going to be my ID that we talked about that defines the relationship. We can use this ID to relate to the census data. So with our census data, right, we also have that community area number. So this is a fun query to write. So let's get after it. Let's see if I can do it live without cheating without looking at the one I did earlier. Select star. Let's start with the from clause. The from clause is the most important. We usually go from bigger table or smaller table. Let's start with the crime table. I think it's, what do I call it? Chicago crime data. There it is. Select star from Chicago crime data, which I'm going to alias as CCD, so we know what this table is. Join the census data, CD, on what is the key? How am I relating these? CCD dot community area number equals CD dot community area number. So we're joining these on that common column. And I can just run this and you can see that it blows up my monitor, but it does return a million rows that are joined. We see the hardship index, which is only the census data, as well as the crime data. So from here, this is now where we can do an aggregation. Let's do a group by. I want to group by the community area number as well as the, whoops, community area name. And then we want to bring back both of those as well as the count of the ccd.id, the count of the crime IDs as the number of crimes. And then let's order by. So many clauses. Oh my God. Order by the count descending. And then we could do a limit 5, I guess, or limit 10. Bring back our top 10 communities. And we can see Austin, Humboldt Park, Englewood are all at the top of our list with the most number of crimes in our crime database. So very cool. There are other ways to do this. You can use a subquery if you want, but I think a join is easier. And yeah, use a subquery to find the name of the community with the highest hardship index. We did that over here. So that's literally the exact same query. We just got to fix our column names. Oh my God. From census data. There we go. And then use a subquery to determine the community area name with the most number of crimes. We already did that as well. I don't know why problem 8 and problem 10 are the exact same. So Austin is your answer to that one. And you can challenge to the reader, refactor to use subqueries instead. Look at that, 215 right on the nose, basically. Cool. And that is the main project here. So long story, just to summarize kind of what you're doing in week 4. With week 4, we're practicing our SQL commands. You should know a couple of things after we get to the end of week 4. First, what is a relational database? What's the history of relational databases? What are relational databases good for? How do you start designing a relational database? That's some of the big ideas at the start of the lesson. Then we went into CRUD operations, your core create, read, update, delete for data engineering and data like warehousing, and your SQL commands for those purposes. How do we create tables? How do we insert and create rows? How do we read or select or query from those rows? How do we update or alter specific rows? And then how do we delete rows and tables as well? After you practice with your CRUD operations, then you'll get hands-on with the actual labs. With the actual labs in 411, you'll start by interacting and creating and querying against the census data for Chicago. In 413, you will create and practice your queries against the public school data for Chicago. Again, both of those are pretty hand-holding. They'll give you the answers in the notebooks. And then finally, your main project is 415 here, 416, 416, which is this mini lab of using 3 tables to write queries and do analytics and things with. So definitely we went through all of that here. My only other note is after you write these queries, right, and get these results, like start thinking like a data scientist, right? Like what are some actionable insights that you can make given these these solutions, right? Does the response match your gut, right, or what you expect? So, for example, I'm seeing a couple. We talked about how this was surprising to me, right? I took a minute to look at the results of my query and interpret them in a data-driven way. Same thing maybe for the community numbers. This is surprising to me that Austin has twice as many as the number 2 spot. Why are there so many more crimes in Austin versus Humboldt Park, right? So maybe that's something you can then follow up with, and you can even like Google it. Like I actually know this Austin neighborhood, and it's like, yeah, it's not a great neighborhood. Yeah, right next to Oak Park over here. So you can kind of see kind of where it's located and kind of what it's near and all those things, right? Parts of Austin, Chicago to avoid. That's the first thing that pops up, right? So now you can like do some extra digging. So again, we never just do data science in a vacuum. You want to also think critically about it. And Michelle, I think that was right on time for you to hop out because I'm pretty sure I have nothing else to talk about. I could definitely take some Q&A and kind of go over some logistics or other big ideas if that would be helpful. There we go, Karen. Anything do you want to add here at the end before we turn it over to Trey or the chat or Q&A or anything?
Oh, have to be muted, unmuted first. I don't know. It seemed pretty good. Oh, I know one question that may come to people's mind at some point with the SQL magic, which I don't usually use because I'm a glutton for punishment. But I'm wondering if you do a query in SQL magic and you get that nice little table, how can you save that like as a data frame?
Yeah, you can. I think we showed kind of one of them where you can actually like, especially if you use the single SQL command, you should be able to save it off. Let me actually see what
So I
this
was
looks
trying to see
like.
where you do that. Yeah. Because I like I say, I'm a glutton for punishment. I write it in Python with all the cursor and everything.
I think it has to be like this, but I also don't know if it'll like it because it's on multiple lines. Yeah,
Yeah, that's the wondering.
I think you got to do it as like, well, usually what I would do is I would actually once let's say you have the command that you like here, that this is the good query
Hmm.
that you want. I save this off to a variable, and then so like here's what my query looks like. You can use triple quotes for a multi-line
Right. Yeah.
string. That was more for tray, yeah. And then we can do df equals pd dot read SQL query.
See, I usually forget to use the panda stuff like that too. Like I said, I'm a glutton for punishment.
Yeah. Oh, this is con with one n. Annoying. And then yeah, and then you can do df2 dot head. So it's the same thing. It just executes it and brings it back as a data frame.
Yeah,
So this is
yeah,
honestly what I usually do in my day-to-day is yeah, you log in a Snowflake or
yeah, makes sense.
Databricks, write the query in the app, and then in your notebook, you then copy the query over and then read it into a data frame.
That makes sense. I'm
Good
just
question.
thinking, but I thought that might be useful for yeah, like the other folks here.
Yeah, definitely good to have on the
So
recording.
ultimately, you want to then be able to do something with the data that you've extracted from the database,
Yep, exactly. That's kind of the last
like
big idea to
database
think about is
logs
that
and
yeah, data scientists should be able to do data engineering work, should be able to do machine learning work, should be able to do business analytics work, creating reports and dashboards. The data scientist is the unicorn in the stack. And in this activity, we've reviewed data engineering as well as kind of data science. And now that it is a data frame, as we'll get to in week 5, next week is where we're going, you're going to be able to use this to start making leaderboards and start making visualizations and then to start feeding into machine learning models and things like that.
I'd say as as being as a data scientist, I think I mentioned somewhere in a comment for someone, it's kind of like you have these different hats to wear, like data engineering is
Yeah,
one,
exactly.
machine learning. But on the other hand, also it could be simply to know enough as the data scientist to know about those different fields so you can interact, uh, productively with other members in a cross-functional team, which is more likely what's going to happen in
Yeah.
a job. So you may
Yep.
not be having to do
Absolutely.
everything, but I have to know enough to be able to talk to the data engineer. I have to know about enough stuff to be able to talk to the machine learning engineer.
Yep, absolutely. Last thing I'll leave you with, then I'll give you all 5 minutes back. If you want some more hands-on practice besides the IBM labs and the kind of workflow in the class, Kaggle Learn, which I plugged every week so far, they do some short little micro courses to get some extra hands-on practice. I actually highly, highly recommend doing it for SQL, also because it doesn't just give you access to SQLite, it gives you access and experience against a larger data cloud warehouse with BigQuery. So it'll actually go through all the same stuff we've done today. We've done all these clauses today. Select from where, group by, count, order by, as, joins. So all of this translates really, really well to what we've done in week 4. And then if you do feel like you have some SQL experience or want to go even further, the advanced SQL class is way out of scope for this class, for this boot camp, but I feel like it's really good. Joins, unions, and subqueries are right here, and then complex analytical functions, and then JSON and semi-structured data in the data warehouse, and then how do you optimize queries depending on different kind of data layouts and data sets, right? So, really interesting way if you want to expand your data knowledge. And like I said, looking ahead to week 5, we're going to be deep diving into Python and pandas for data analytics. So we're going to be going into, again, making those leaderboards, doing some data cleaning and aggregations with pandas, a bigger deep dive into pandas. All right, that's all I got. Trey, Karen, thanks for the time this afternoon. I'll post this to the forums, and I will see you all next week. Unless there's any other questions or concerns, happy to take them now.
Yeah, I've got the remarkable timing of the weed eater guy or the vacuum blower guy. So sorry I can't
All
be.
good, man.
But no, this is great. Thanks. Appreciate it.
Yep, appreciate you being engaged. And yeah, just I do feel like there's a lot of value in these live sessions. If you can find the hour and a half a week to either watch the sessions or participate, and hopefully more of the class does the same. All right, we'll see you in the forums, and feel free to ask whatever questions you have, and we'll see you there. Thanks all.
Well, that was good.